is Crichton, and I'm going to talk to you about today concurrency in Rust and kind of what that all means. It's going to be kind of different from the Elixir OTP talk. This is more kind of like lower down in the stack and talking about kind of like similarities with C++ and C multi-threading and concurrency and things like that. So I want to start out by kind of just talking briefly about what is concurrency. Like, what does it mean to talk about concurrency? And I just Googled literally what is concurrency, and this is what came back out. And basically what it is kind of lots of things flying around, running around at the same time. But the key aspect here is the same time. When things are running in parallel. You have two threads of execution that are actually doing something simultaneously. And so today that's with multi-cores and things like that. And this is where there's a distinction between parallelism and concurrency. And in my mind, I think this is, I always get them mixed up, but I think this is the one where they're actually happening simultaneously. But we'll talk mainly about that today. So the next thing is, why does anyone care about concurrency? Like right now, we all have super powerful machines. Like, why can't I just run my thing on one core and call it a day? And the reason is this whole lack of Moore's law. Moore's law was there for a while, but now it's not there anymore. And now everyone has 64-core machines in their laptops and things like that. So this is a very real problem today, and this is a very real thing which everyone new to programming actually really needs to be introduced to. Because a lot of times, everyone starts out kind of running on one thread. They don't have to worry about a whole lot of things. But then very quickly, you run into these problems of once you start having a concurrent application, you have tons of problems, tons of things arise. And so it is my personal belief that in today's day and age, concurrency, knowledge about and familiarity with concurrency is a must-have in every kind of programming. And I'm going to talk about some of these sample errors. So in general, concurrency is seen as a very hard topic. There's very difficult things inside of it. And this is a really, really simple example where it's kind of a small amount of concurrency, and the question is just, what does this print? And the answer is, well, it could print, so fork is, if you recall, the one that returns 0 or the number of your child. So it could return one of two things. So this could print 0 to number, or it could print number to 0, or it could even intermix everything and maybe print two new lines at the end, depending on the kind of buffering that's going on with the standard out at the time. So it turns out that even just answering this simple question is pretty hard in a concurrent setting. And this is kind of just a bit of an idea to get you used to concurrent programming and what can be difficult about it. The next really big thing which plagues every single person who's ever touched any concurrent aspect or parallel aspect at all is something called race conditions. And this is kind of, again, I just Googled what is a race condition, and this is the formal definition, but it's basically summarized by, I expected it to happen this way, it actually happened this way, which is totally separate. You totally didn't expect that, and it probably caused a crash or a deadlock or something like that. So race conditions are, you always must consider them when dealing with concurrent programming, and you always have to work around them and always expect it. And concurrency is where you have to plan for every single situation possible. And the problem is that state space in every single situation possible explodes really, really rapidly. So it's actually very, very difficult to deal with race conditions kind of on a general level. So if we take that idea of race conditions, that's a very broad topic where you can have races in essentially everything. We'll kind of like shrink it down to something just called data races. So data races is something unique to kind of very low level dealing with the hardware, dealing with compilers and things like that. I doubt, or you definitely don't see data races when you're probably at the level of like Elixir and OTP and kind of like sockets and databases and things like that. This is when you're dealing with just the raw hardware on the machine itself. And so this is the definition of data races that I've come to know, and it's basically two concurrent accesses to the same memory location, which is crucial. Those two pieces are crucial to this. And the next two is one is unsynchronized and one's at least a write. And I'll talk a little bit more about those in a bit. But data races, in general, are where C compilers, if you have a data race, it's undefined behavior. And what that means is it could turn your computer off, it could make pigs come out the printer, it could do anything, it could turn your printer on, it could fax random things places, like anything could happen with the data race and undefined behavior. So this is something that everyone wants to avoid. And because Rust is a compiled language with LLVM, this is something we really, really want to avoid. So one of the final things that I'm going to talk about is deadlock. So this is kind of your canonical, I'm running a banking server and I have two accounts and I want to transfer money from the from to the to. And so the first thing I do, well, I want it to be atomic. I don't want to make sure that I like pull out the money of this guy's account and the whole system crashes and then I lost that money for forever. So what I'm going to do is I'm going to lock the first one, I'm going to lock the second one, and then I'm going to switch the balances, and then I'm going to unlock them. The problem with this is it looks pretty innocuous, and if you're familiar with mutexes and things like that, you're like, oh, okay, this is probably not going to have any race conditions, probably not going to have any data races, but the problem here is deadlock, which what it means is if I call this function with accounts 1 and 2, and someone else calls it with accounts 2 and 1, we get a very quick deadlock where one person grabs the 1's lock and one person grabs the 2's lock, and then neither one can progress. So deadlock in general is where you have a lot of threads, actors, whatever in a system, none of them can make progress. They're all in contention over the same resources, and no one's willing to release a resource. So this is another big problem that comes up with a lot of concurrent programming. So to kind of summarize, a lot of these bugs can lead to things like cyc faults used after freeze, double freeze, deadlock, starvation, spinning. And I didn't talk about all these in detail, but one of the big things is every single one of these is exploitable. Which means if you have, like let's say you're writing up an SSL, and all of a sudden you're like, oh, I have 4 cores, let me actually make use of that, and decrypt all the incoming connections on 4 cores simultaneously. It's actually really hard to do that. Because how are you certain, 100% certain that you do not have any data races, you don't have any race conditions, you don't have any of this? Because if you do, you're all of a sudden a very exploitable piece of software, and you probably don't want to be if you're an SSL. So now I'm going to talk about where does Rust come into all this? So this is Rust's pitch on the website currently, which is Rust is a system programming language that runs blazingly fast, prevents almost all crashes, and eliminates data races. So there's 2 key aspects to this that I'm going to be kind of focusing on in this talk, and that is preventing all crashes and eliminating data races. So I showed you earlier that those were kind of the two banes of concurrent programming. That's where a lot of bugs come from, cyc faults, crashes, all these fun things. So Rust completely eliminates them, making them impossible to write in general safe code. And so I'll talk a little bit about, for a second, a little bit about Rust, and you'll notice these playpen links at the bottom. If you go to that URL, you can actually click on them, and then it'll run it in the Rust playpen, so you can kind of play around with this later if you want, kind of play around with the examples. But anyway, this is kind of just a taste of Rust. Not a lot of types, C-looking syntax. We've got some threads running around, some printing, just kind of see what it looks like. You can kind of see some concurrency going on with the spawn is actually spawning a parallel thread of execution. So one thing which is really, really big to Rust, which is actually kind of the core foundation of Rust that essentially everything else is built on, is ownership. And ownership is the concept that every single piece of data is owned by one person at all times. That's it. It's a very simple concept from which I'm actually going to talk about how this leads to safety in the rest of the language. It leads to actually preventing all of these bad concurrent bugs. So with this ownership, this example is it creates a new vector, puts it on the stack, it pushes a new thing on it, and then it drops it. So drop is kind of the Rust way of saying go deallocate this and don't worry about it anymore. And so then afterwards, I attempt to push on that. So that's actually a use after free if this compiles correctly, because this vector was dropped at this point, and then I'm trying to push on it afterwards. So like in C or C++, this would actually compile just fine, but then you would have a cyc fault afterwards. You would hopefully have a cyc fault, and everything would die. So in Rust, we have this concept of the stack, the local variable v owns the vector, and then you can kind of do some stuff to it, and then you release ownership of the vector by passing it to this drop function, and then you can no longer use it. So I'll come back to ownership a lot throughout the rest of this, but you can kind of think of ownership as just one person owns this, and then some other people can borrow access to it, but they never actually acquire ownership unless you kind of relinquish it along. So the other really big part about Rust is it's totally safe. As the pitch was saying, Rust is a language built for safety in these low-level concurrent aspects, low-level building blocks. So Rust does all this by not actually putting all this in the language. All of this, the ownership, the borrowing, kind of these core fundamental language features allow us to write safe libraries and safe abstractions, which give you the tools you need to write totally safe concurrent code. And so the big takeaway from this is the Rust language itself is actually really not all that complicated, but the Rust libraries are where the really big amount of logic happens. That's something which we found to be really, really powerful over time to kind of not make it so much about the language giving you these fundamental like concurrent or spawning or channels or anything like that, but the libraries are actually doing that. So I'm going to talk a little bit about all these concurrency primitives that you have to play around with in Rust, because we have a good array of primitives which can help you in various situations, which you'll see a lot of parallels to this in C++ and Java Go and lots of other languages with concurrency and things in them. So the most basic of these is just spawn. Spawn is like pthread create or go, or just creating a new thread of execution. And so all this is doing is it's spawning hello world. You can see if I run it here, in this case I saw world hello, but it's like in some cases you might see hello world depending on what your computer is feeling that day. So the next thing that we give you is something called channels, and channels are Rust's manifestation of message passing, if you're familiar with that. And the idea with a channel is that you call this function called channel, which gives you two endpoints to the channel. One, the T-axis is the sending end, and the R-axis is the receiving end. And then what we do is you can also clone the sending end, so you can have multiple people sending to a channel. So in this case, we spawn two subtasks that are sending on the same channel. Clone is kind of cloning a reference to the channel, not actually creating a new channel. And the first one sends 5, the second one sends 4, and at the very end, we print out what messages we just received. So this is another case where we might see 4 then 5, or we might see 5 then 4, and this time, it turns out we actually see 4 then 5. You might see results maybe. But so channels are totally generic, so you can send any kind of message over a channel, you can send anything you want. And the idea here is that you take an object and you give ownership to the channel, and then later on someone can receive ownership of that object back by calling receive on it. So this concept of I'm taking things and moving them into the channel so I relinquish ownership of them, and then later on someone else in a concurrent aspect might get the channel at the other end.
On channels, can you define their configuration, like if they're buffered or if they're blocking or not blocking, that kind of stuff?
So right now, we have two kinds of channels, where one is asynchronously sending, or one is essentially infinitely buffered, and one is synchronously buffered.
Okay.
And what that means is this one, the default channel function, every time you send, you're just going to keep sending and sending and sending and sending, and it's just going to have a big queue of things, so it's essentially asynchronous. And then we have another one called sync channel, where you can create it with a bounded buffer, and then when you attempt to send on a bounded channel, it blocks.
Okay.
So you have these two distinct. We have those two flavors of channels.
It blocks when it's full or it blocks all the time?
Blocks when it's full. You can create it with a zero buffer as well, which means you atomically hand things off, and only if someone else gets it. So another thing that we allow you to do with channels is selection over them, and selection is just a way of saying I want to wait for all these channels, but just telling them one of them wakes up. So in this case, we're listening on two channels, and depending on which one we receive first, we're actually going to run that block first. And this is kind of select is the way you kind of compose channels together and kind of build your application from many channels from many places. So another thing which Rust has, which is not unique to Rust, this is the equivalent of shared pointer in C++, if you're familiar with that, is arc. We call it arc, and it stands for atomically reference counted pointer. And what all that means is it's just a reference counted pointer, but the operations on it are atomic, so it's safe to share across threads. So in this case, what I'm doing is I'm putting a vector of 3 numbers into an arc, a pointer, and then this shared numbers thing is actually just a pointer. That's all it is. So it's a pointer to this arc, and then I clone. What that does is it creates a new reference. So child numbers and shared numbers actually point to the same data. There's no copying going on. So clones are very cheap operations. And then I move one of them into the child, and then I leave one of them on the outside, and then everyone can access it at the same time. So arcs are how you share memory in Rust, which is distinct from message passing. In message passing, there's not a whole lot of sharing. You're just sending things from place to place. But a lot of times you might have like a very large data set. You want to share among a bunch of tasks. You don't want to have to bother sending it around, so you can just straight up share it. And I'll talk a little bit more about this in safety a little later on. Rust provides low-level access to atomic primitives. So in this case, I'm creating an atomic integer. There's not a whole lot of parallelism here, so it's not very interesting. But these operations mean that you can modify this atomic integer across multiple threads. And I'll show you how you can do that a little later. But you have basic operations like fetch and add, which will atomically add one to it and then return to the previous one. You can swap. You can do atomic operations like load, store, things like that. And then one of the last things I'm going to talk about here today is mutexes. And mutexes are things that I'll find in essentially every language that has threads or anything like that. But one of the things that's kind of a little bit unique about Rust mutexes is when you acquire a lock, it actually represents a resource inside that lock. So in this case, whenever I create a mutex, I actually create it with the resource that I'm protecting. In this case, is that vector 123. And then inside this kind of sub-scope, I'm going to acquire the lock and then push onto the vector. And what this is actually doing is, this lock is returning in something we call an RAII substructure. And all that means is that at the end of this block, it's going to get unlocked. So in this case, while I have the lock, I have access to the vector. But when I don't have the lock, I don't have access to the vector. I just cannot access it. So this is a way that Rust protects you from accessing something outside of a lock, where it's kind of easy to do if you're just using like pthread mutexes or things like that, because there's no concept of what they're protecting. So this is where Rust is using the language and the ownership ideas of protecting these resources, because the mutex owns the vector, and you cannot get access to it unless it allows you to have access to it, and it only allows you to have access to it once you already grab the lock. So we in general have a big wide array of libraries and fun things. All StudSync is the module that we have everything in. You'll find stuff like barriers for having tons of threads synchronize at one location and then go on. Our DEADLOCKS for grabbing reader and writer locks. Semaphores, fun for all tons of things, and then onces are this fun primitive where you give it a function and it runs it once, but every future person will never run it again. And it's a pretty efficient way to do concurrent initialization. So now I want to kind of dive into why does Rust have no data races? I've talked a little bit about what a data race is, and I've shown you some of the primitives. So I want to kind of review again what a data race is. And a data race has these key ingredients, where one is concurrent access, which Rust definitely allows you to do. Rust will allow you to run things concurrently. So we have this danger already. We might be having data races. But one of the big crucial points of the data races is the same memory location. And with ownership, it turns out that's actually kind of hard to have. That's kind of hard to happen, so you have to explicitly opt into it, which I'll show you. And then I'll talk a little bit more about these, one unsynchronized or one is a write, and how we can prevent these. And the goal is to totally prevent data races, which prevents undefined behavior, which prevents crashes in Rust. So if we go back to thinking about ownership, this is kind of a classical case of where in C++, if I did this, it would compile just fine. And most of the time it would work, but most of the time it also wouldn't, in the sense that this vector is being shared among a child thread and the main thread. So this vector is being concurrently modified, and it's being concurrently written to by pushing things on this vector. Now, things in Rust aren't protected by default, so this is like vec is not a thread-safe primitive. You cannot push onto it concurrently. But because of ownership, this won't actually compile. And what happens here is this thing called a proc is called a procedure in Rust, and procedures are kind of like a closure, if you remember that from other languages. But this closure consumes ownership of anything it closes over. So in this case, this vector v is moved into the procedure. So the procedure now owns it, and then this outer thread no longer has access to it. So this fails to compile because the outer thread is using a moved value. So this is a case where, by default, there is no shared memory, which is really, really powerful in terms of Rust, because that means this entire, that whole class of data races is all of a sudden gone because we don't have any shared memory. Now, it turns out that's not very, very useful, because a lot of times you do want shared memory. I showed you earlier that you can actually have shared memory with arcs. So this is kind of the same example from before, where the arc is a way you give ownership to this arc, and then you clone it along and you move it into some test, and you can access it concurrently. I can look at the length, I can look at whether it contains things, and this is lots of reading access. So a question you might have is, well, it's not very useful. Like, what if I just put an arc around this vector and then I just pushed on it? That's the exact same problem. There's no synchronization. An arc is just a pointer. And so it turns out if you try to do that, Rust also disallows that. So if you do that, where you take this vector, you put it into an arc, and then you attempt to modify the vector, Rust gives you this error that you cannot borrow an immutable dereference of an ampersand pointer as mutable. And all that really means is Rust has these two pointer types, an ampersand and ampersand mute, which is a shared borrow and a mutable borrow. So this push function naturally requires a mutable borrow because you're modifying the container. And arcs only allow you to get a shared reference out of it. So this means that all of the methods on vec, which require a mutable reference to itself, don't work. So what arc is essentially doing is giving you read-only access to the data inside of it. Now that read-only, I'll kind of give that a caveat in a second, but this is the unsynchronized write that I was talking about. If you have just essentially any sort of modification of a memory location, unless you're doing it atomically, that's an unsynchronized write operation. And if we go back to the top, you can see that ingredient for a data race is 2 concurrent accesses, which we've got. We got things running in parallel over shared memory at the same location, which we've got because we have arcs. And then the next requirement is at least one is unsynchronized. So we ban that right now. There is no, we're doing the write, where there's no writes to this memory location right now just yet, because arcs only allow you read-only access into the insides. So again, that's also not very useful. If I can only read a bunch of shared state, I really want to be able to modify that from time to time. So Rust does allow that through things, again, in a protected manner through things like mutexes. Mutexes are explicitly designed such that when you can share them across many threads, and then you can lock them across many threads, and then you can kind of do all the things with it as you normally would. So what this is doing is, the first thing is I'm creating a vector, I'm putting it inside of a mutex, and I'm putting all that inside of an arc. So what I have now is an atomically referenced kind of piece of memory with a mutex inside of it with a vector inside of that. So you can kind of see this is a lot of composition going on here. These primitives kind of all building on top of one another because you get to our final product. But the key idea here is everything is kind of owning the inside. And once you own it, you get to choose how you allow access to it. So in this case, in this sub-procedure, we actually grab the lock and then we push something onto it. And that will, because locks are thread safe and synchronized, we're allowed to, that mutation is safe, because this thread cannot even access the vector unless it has the lock. So we can, if we go back to that original slide, you can see that these unsynchronized operations, like this is an unsynchronized operation, but it can happen exclusively from this because of the lock happening around it.
Can I try and generalize that? I just make sure I understand it. So
Sure.
If you want to allow concurrent reads, you only need to wrap an object or a piece of data in an arc.
Yes.
If you would allow reads and writes, you need mutex.
Yes.
Every arc.
Yes.
Okay.
Which is, if you think about kind of best practices with concurrent programming today, that is what you would do. That is the only way to make access to a vector safe, is to put it in a mutex. That's the only way. And then if you want a more efficient access, you can have an RW lock, which allows many readers, more than one writer, things like that. So this is where we are taking kind of conventional wisdom around these primitives and making, yes, in the library, it's impossible to use them incorrectly, which is the great power of Rust, is making it impossible to use incorrectly.
So there's some syntactic magic going on here. Like a.lock is a method of mutex. So can you explain how
Yeah.
to do that?
So let me actually run this. I can show you that the type of this local variable is actually arc, mutex, event. That's it. So what this is actually, this is a very layered object where the inside is what we're accessing. So this .clone method is only cloning the arc. It's not actually cloning the mutex of the vector or anything like that. So it turns out this local variable is also an arc of the mutex of that event. So what this is doing, there's no, like, arcs do not know how to lock themselves. That doesn't make a whole lot of sense. So this lock method is not actually being applied to the arc, but the Rust has this deref trait, which basically what it means is if I'm an arc, which is essentially just a pointer, I can go to the inside and I can call methods on that without any other syntactic sugar or anything, or without any other things going on. Like, you can just do it. It's a sugary way to do it. So this way, this is actually calling the lock method on a mutex. And then what that's returning, this is actually kind of a fancy thing called a mutex guard. So I won't go too much into this lifetime syntax and things, but it turns out this is actually an object itself. And so when this goes out of scope, it's going to unlock the lock. And then this is the innards. And then when you call that push, it's not actually calling push on this, it's calling push on that.
Since the mutex guard also implements deref.
Yes. So there's some syntactic sugar going on here to make this actually pretty nice to read and take away all the type annotations. And all of these objects are kind of known to be just pointers to the insides of other objects, and then they might do have some other fancy things around them.
What does the apostrophe A mean?
Not ticking.
So this is what we call a lifetime in Rust. And a lifetime is, I alluded to borrowing, where from an own thing I can borrow a resource. And if you think about it kind of conceptually, if I borrow something, it's only valid while that thing is still there. So it's like, this borrow is valid for a very specific lifetime. And that's kind of the conceptual way to think about it, and then it's actually manifested in terms of these ticking all over the place. But I'll talk more about that later.
Okay. And that deref tree, that works for any generic types down the chain, like
yes.
in Rust or in. Cool.
And you'll note that, well, I'm just going here. Mutex does not implement deref, because in theory, mutex could it's just containing the inner thing, but it knows that that's an unsafe operation. So mutex explicitly does not do that by design, and that way you cannot access the inner vector without locking it. That's the whole point. But once you've locked it, you can do whatever you want with it. So that's why the lock implements deref, but the mutex itself does not. All right. So I'll go over this one last time, and I can kind of show you how we have completely eliminated data races with these library abstractions and this concept of ownership. So we have the preconditions of 2 memory accesses to the same location. We definitely have that. And at least one is unsynchronized. Well, we do have that because mutexes do allow unsynchronized access to the same location, but they always do it mutually. It can never happen at the same time. So we don't quite have that for data races. And the last one is at least a write. And the critical part is that these never happen at the same time. You have to have both of these to happen. Sorry. Yes. Well, each one of these can happen independently of one another. But these 2 memory accesses I'm talking about is you can never have 2 unsynchronized memory accesses where one of them is a write, and you can never have 2 memory accesses, both of which are writes, unless they're atomic, in which case everything is all fine. So I can go into some more details later, but in general, the primitives in Rust actually prevent all the data races from that. So another thing that I was talking about, which is plagues a lot of concurrent programming, is double freeze, where a lot of times you're not actually sure when this resource goes out of scope. So someone else might free it, or you might free it, or you're not totally certain. So Rust also prevents this because it's a safe language. That its goal is to prevent these crashes and things like this. And again, this is where we really leverage this idea of ownership, and the idea is when a resource goes out of scope, that's when you free it. A resource can only go out of scope one time. So that's kind of the key aspect to ownership is if you have that guarantee, you actually don't need to worry a whole lot about double freeze. You don't need to worry about a whole lot about memory management and things like that. You kind of create the memory, but then someone else goes and takes care of it from you after that point. So because we have this concept of moving around and everyone is always owned by someone else or they're free, then we don't have to worry so much about double freeze. And you can see that with arc as an example. Arcs have this reference count associated with them. So we know that when we first create it, it has a reference count of 1. If we clone it, it has a reference count of 2, because now there's 2 references to it. And then when we're going to drop one of them in the one thread, we're going to drop one in the other thread. So either one of these might actually drop and free the resource, but all we need to know is that when it reaches 0, it will be free. And when that reaches 0, it's actually going to free the inner vector. So the inner vector will always be safely deallocated because it's only deallocated when the arc itself is deallocated. And then we're not actually sure who's going to deallocate it. It doesn't actually quite matter, but we know that it deterministically will happen at some point when it needs to. So when you combine no data races and no double freeze, you get no site faults. And this is the holy grail that Rust is kind of approaching and running after is no site faults. So with all of those combined together, Rust can give you a concurrent model of concurrent primitives, but you can't site fault. So a lot of times, if you're kind of daunted by writing these big applications with lots of concurrent aspects to them, it can be, you can stop very, very quickly saying, oh, I'm not actually sure if this can site fault. I'm not actually sure if this is safe. But in Rust, you know that if it compiles, it's safe. You don't have to worry about it. So this is where that's kind of the safety in Rust is absolutely paramount. It is the primary goal of Rust is to give you all of this safety and prevent crashes, but while still allowing you raw access to these concurrent situations and all of these contexts, which is really, really critical for a lot of applications. So I didn't really talk a whole lot about deadlocks and starvation in terms of Rust, and it turns out we do still allow this. But the good part is that this is not. This is a less severe condition. This is still exploitable in some sense, but it's much less exploitable in terms of arbitrary code execution or things like that. So we have, in the past, attempted to prevent deadlock by actually just having static analysis in the type system, but it turned out to be so limiting, you couldn't really do a lot of useful things with it, so we ended up just ripping it out. So our position today is that the Rust type system is not powerful enough to actually prevent these two situations, and it may be able to in the future, but for now, the way that it's currently designed is it's too limiting if we actually leverage it to try and do this. So you can still get into a deadlock with Rust. You can still starve it. You can starve readers and writers in Rust and things like that. But these are not considered unsafe operations. These are just kind of considered application errors. And if you think back to the beginning, it's kind of fall under race conditions as well. We don't prevent race conditions. I can still make a database connection, make a TCP socket, and then accidentally mismatch what's being sent on one or something like that. So Rust, the type system in Rust cannot prevent that, but that is arguably much more an application error than the actual, and it's less exploitable than data races and things like that. So that's all I have. We have tons of links. You can find all of this, all open source, all online at just GitHub. We have a website and an IRC channel, and remind me that I have stickers, because I always forget that I have stickers. I wrote on a slide that I have stickers, so I have stickers. All right, any questions?
So just as a quick overview, if you were building up the read-write logs from the primitives, so from Marx and from Regenesis,